We've already talked about matrix multiplication in terms of multiplying matrices times vectors, and we know that we're supposed to take the dot product of each row with the vector. So now we're going to extend that to the entire matrix. So the important thing they're showing is that they're giving the notation, right? So if I have component A sub ij, so this is in matrix A, right? If I have a matrix A, capital A, I use little a with double subscripts to determine its components, right? I refer to its components as lowercase letters, the same lowercase letter. And so the jth column, right? So the second index there is the column that it's in, and the first index is the row that it's in, right? So all of these on the top have the first index is 1 because they're in the first row. And they're pointing out that we were just multiplying the columns of, we were just multiplying matrix times columns. All right, so here's the important idea about when it's possible. It's not always true that the matrix product is defined. They have to be compatible matrices. And to be able to multiply them, the number of rows has to equal the number of columns. Okay, so look at this. M by N matrix and an N by P matrix can be multiplied together, and I get M by P. So let's look at that. We call what a lot of math majors learn is that, or math and science majors learn, is that if the inner product dimensions match, right? So if the number of columns in the first matches the number of rows in the second, then I can multiply the matrices, and the result will be the outer dimensions, right? So we had an M by N and an N by P, so the resulting product matrix is M by P. The way that people normally think of multiplying matrices is they find the entry of the product matrix, right? So the product matrix is C. This is the first matrix A times the second matrix B. So this is times A times B equals C. Then the C sub ij entry in C is the dot product of row I in A, right? The ith row right here, with the jth column. I just take the dot product, and that's what they're showing here. So to get the C sub 1, entry, I'm going to dot the first row of A with the first column of B. And to get another entry in the first row, I'm going to take the first row of A, right? So every one of these values in the first row, I'm taking the dot product of the first row of A with the columns of B successively. Now when we're multiplying, there's a couple of things to notice. AB is not usually equal to BA, which you can see, right? What if I have a matrix that's a 2 by 3 matrix and B, so I'm doing, these are the matrix dimensions. I'm just thinking about the matrix dimensions here. And let's say I had a 3 by 2. Right? So if this one's A and this one's B and I multiply them, I end up with a 2 by 2 matrix, the outer dimensions, right? The inner dimensions match 3 and 3, and the outer dimensions will be the resulting matrix. But what if I do it in the reverse order? Well, if I do it in the reverse order, I have so let's get rid of this. So now I'm just looking at B being multiplied by a 2 by 3 matrix. I can still multiply them. This isn't always true, but in this case it is. The inner products match, but now I end up with a 3 by 3 matrix. So when I multiply them in one order, I get a 2 by 2, and when I multiply them in the other order, I get a 3 by 3. So that's what we mean. It's not usually equal. Sometimes they're not even the same dimensions, but even when I have square matrices, it's not usually the case that multiplication is commutative. So you need to be careful about that. And because multiplication is not commutative, um, it does not satisfy the cancellation law. It doesn't mean that just because A times B equals A times C, it doesn't mean that B equals C. And they show an example here, right? A very simple matrix where they're both equal to this, but notice that I have a difference in matrix B, okay? So you can't just assume that the cancellation law holds. It doesn't. Sometimes, I mean, it could hold, but that's just a coincidence. It's not a law. It's not the cancellation law. It's the cancellation coincidence because it's not always true. And then this is a weird one because we have the zero product property for real numbers that says that if I have two real numbers, x times y, and they're equal to 0, then we know that either x is equal to 0 or y is equal to 0 or both. Well, what they're saying here is, ooh, the zero product property does not hold for matrix multiplication because we could have a non-zero matrix A and a non-zero matrix B, and they could be equal to the zero matrix. So you have to be very careful. These properties of real numbers, like the commutativity of multiplication and the cancellation law and the zero product property, yeah, they're fine for real numbers, but arithmetic with matrices doesn't work that way necessarily. And as always, I'm going to caution you to read this section very carefully. They go over the properties of addition and scalar multiplication for matrices, and it's these are the things that are true. Addition is commutative. I can add in either order. And scalar multiplication distributes over matrix addition. And scalar multiplication is commutative. I can do it in either order. Addition is associative. The scalar sum, you can either sum the two scalars and then multiply by the matrix, or you can kind of think of this as the matrix multiplication distributing over scalar addition. Now this is cool. When I do add the 0 vector to A, I get 0. So we do have the additive identity plus any matrix is just equal to that matrix. So those are properties that are true, as opposed to the ones we were talking about above that were caveats that are usually not true. And then for matrix multiplication, matrix multiplication distributes, right? So I can do A plus B and then multiply by C on the left, or I can multiply A by C on the left and then multiply B by C on the left and add those. So that works. Scalar products will be fine whether I do the matrix multiplication first and then the scalar product, or if I scale one or the other vectors, one or the other matrices. And we also have the identity matrix. So the multiplicative identity times any element is just that element. It turns out that matrix multiplication is associative. If you can do all of these multiplications, A times B and then the product times C, if all of these are possible, right? That's what they're saying. If everything in every multiplication that's described here is actually possible, then this is true. The matrix multiplication is associative, and it distributes, right? But notice that it's important that it be on the right. This is left multiplication distributes. This is left, right? This is not true, say, if this were BC, right? Why? Well, because matrix multiplication isn't commutative. So this may not be the same thing. BC may not be the same thing as CB. And this is important that the C is always on the right in these expressions here. So yes, matrix multiplication does distribute over addition, over matrix addition, but only if I keep the multiplying matrix in the right place. Again, scalar products behave very well, and it doesn't matter whether I multiply by the identity on the left or the right, it will always result in the matrix in the same matrix that I started with. What's different here is this is I sub m, and this one over here was I sub n. And why is that? Well, if I'm multiplying on the right, the identity matrix that I need to use has to have the same number of rows as A has columns, right? So this n m by n matrix, that's why it's I sub n on one side and I sub m on the other, because now I sub m has to have the same number of columns as A has rows. So the identity matrix works, but they may not be the same identity. If when I multiply on the right, I may be multiplying by a different identity than when I multiply by the identity on the left. So I'm going to switch over to MATLAB now and show you a couple of things. These are actually the same four matrices that we used in the prior section, but now let's talk about multiplying them. So we said that if I'm going to multiply A times B, right, that to get, so let's say that the product matrix is P, right, then the P sub 1, 1 entry is going to be the row 1 of A dotted with the first column of P. All right, so let's see if we can make that happen. So let's do P sub 1, 1 equals the dot product of, let's see, so A, and I want row 1, and B, I want column 1. Okay, so they're saying that's 77, and let's just check to see what we get. We have 5 times 0, which is 0, then 7 times 8, which is 56. So this equals 0 plus 56. And then 7 times 3 is 21. And then 1 times 0 is 0. So you can see that we do in fact get 77 if we just do the dot product of these two rows. Okay, so we can keep doing this. What's the row 1, column 2 entry of the product matrix? Well, that's dotting the row 1 from A with column 2 from B. All right, so now P, you notice it just added on this additional entry, the NT. So now let's get some of the other rows, right? What if I would do 2, 1, right? Well, that's going to be the second row of A times the first column of B. And you can see that we have, it's added a whole new row, but it threw a 0 in here because it doesn't know what that is yet. And we're going to do it by saying, well, the second row, second column entry of this is going to be the second row of A times the second column of B. All right, and you can keep going with that. And there's a lab to practice. And it will, in fact, be what's equal to oh, I'm sorry, we did the whole thing, right? Because we had a 2 by 4, right? A is 2 by 4, and B is 4 by 2. And the inner products match, so we can multiply them, and we know the resulting dimensions will be 2 by 2. All right, and just notice that when I multiply in the opposite order, right, I get a 4 by 4. Okay. So what about C and D? Well, C and D are both 3 by 3 matrices, so we know we can multiply them in either order. And again, the product matrix is going to have the product matrix entry 1, 1 in the product matrix is the dot product of of row 1, row 1 in C dotted with the first column of D. And let's try that. Oh, let's see. So, I think the empty matrix is that. There we go. So that just returned P to the 0 matrix. So now we have the 47, and let's just verify that we know what's going on. If we're multiplying C times D, we're taking the first row of C times the first column. So we have the 7 times 7 is 49, 0 times 5 is 0. So we have 49 minus 2, which is in fact 47. Okay, and to get the next entry, right, to get the P12 entry, the one that goes in the first row in the middle column right here, we still multiply by the first row, but now we're multiplying by the second column. So we have 49 plus 8, which is 55. And we can verify that by taking the first row of C times the second column of D. I'm sorry, 49. Yeah, 49 plus 8 is 57. I'm sorry, I added 6 and not 8. But you can see what's happening. So these dot products are how I do the matrix multiplication. I just have to do one for each possible row. I take each possible row and I multiply it by each possible column. Right, so since for the first row I'll have 3 multiplications that I do, I know that this is going to have 3 columns, and since for each column that I can multiply it by 3 different rows, I know that I'll have a 3 by 3 matrix to multiply. So it's not that hard. Addition is really easy. Addition just happens component-wise. So if I take my C plus D, right, then it goes entry by entry, but the entry in the sum is just the sum of the two entries, 7 plus 7. If I want to know what the sum is in the bottom right corner, I add the bottom right corner of C and D together to get -4. If I want to see what the value will be in the top right, I add the top right of C and D together. All right. And then scalar products are what you would think. You just multiply all the way through. So if I have this matrix C, then 3 times C just takes every single component of the matrix and multiplies it by 3. Now the zeros multiplied by 3 are still 0, but when I multiply 3 by 3, I get 9. 7 and 4 times 3 are 21 and 12 respectively. So this section was just about how to multiply and do actual matrix multiplication, but they also mentioned scalar multiplication and matrix addition in this section as well.